Hi and welcome to this video. My name is Sven and today we'll talk about affine, conic and disjunctive constraints in the upcoming MOSEK version. Let's start with a little bit of background on MOSEK. MOSEK is an optimization software package for solving large-scale linear and conic optimization problems. It also lets you solve convex quadratic problems, and in many cases mixed integer versions of all these problem classes. What MOSEK really is about, though, is conic optimization. In fact, quadratic problems are, at least in the current version, always converted internally to conic form. And also linear programming is actually just a special case of conic programming. Or said differently, conic programming is the extension of linear programming that preserves most of its nice properties, such as Lagrangian duality theory. You can see here, for example, a conic primal and dual pair in standard form, where the dual always has an explicit representation, just as in linear programming. The generic cone K here can take on the form of several different cones with more concrete descriptions, or it can be the Cartesian product of several low-dimensional such cones. That's what actually happens a lot in practice. And here is a list of the building blocks available in MOSEK. The simplest cone one can think of in this context is just the non-negative orthant, giving rise to linear programming. Also very prominent is the quadratic cone family, largely used for modeling anything that contains Euclidean norms or convex quadratics. The semi-definite cone, here described with matrix variables, has many classical applications in convex optimization, but it can also appear in real-world applications arising in engineering, or as a means to build strong relaxations of some combinatorial optimization problems. Now, the three previous cones are the well-known and very well-behaved from a mathematical point of view, so-called symmetric cones. And MOSEK also supports two non-symmetric cones, the first one being the exponential cone. This building block allows you to model many constructs containing exponentials or logarithms. Also supported is the power cone that lets you model p-norms or convex rational powers or similar things. The power cone, by the way, as you can see here, is the only cone in MOSEK that requires a parameter alpha. It is by now common knowledge that the 5 cones we have seen here are enough to express, sometimes with a certain amount of reformulation, a vast majority of the problems arising in convex optimization. There are still other cones of interest though, and some may become available in MOSEK in the future. Let's now have a rough look at the interfaces to the algorithms implemented in MOSEK. There is first of all the rather low-level optimizer API, available in several languages, and in addition to some further interfaces, MOSEK ships with its own modeling language called MOSEK Fusion. Now, Fusion is an object-oriented modeling language specifically designed for conic optimization, and thus making it particularly easy to handle cones in optimization models. However, the core of the MOSEK package is the good old C API, and all other APIs are built on top of it. And today we will talk about the changes that we made recently to precisely the C API. And these changes will be released in the upcoming MOSEK version 10. Now what happens in MOSEK 9 right now is that cone membership can be specified for the variables directly, or of course for only a subset of them. And that's exactly what's needed to write down a model in standard primal form, for example. And what you cannot currently do is write down cone membership for an affine expression of the variables, as it would appear in dual standard form. Yet the current interface is in principle very general and doesn't stand in the way of the modeling versatility of conic optimization that we proclaimed on the previous slide. And that's because you can always introduce as many auxiliary variables and linear relations as you like. As an example here, take the Euclidean norm of the error of some linear system, which is something you would encounter when performing least squares regression. In order to specify cone membership for the error itself, you just need to model it with an explicit auxiliary variable. In some cases, however, this can be cumbersome, And the primary goal of the redesign of the C API was to be able to specify cone membership for affine expressions easily. Now, if you are a Fusion user, then you are already able to write down affine expressions into a cone directly. So these changes don't affect you in terms of usage. Still, they affect you under the hood, because all APIs, also Fusion, are routed through the C API. And one advantage of the upcoming redesign is also that the Fusion model and the Optimizer API model come much closer together, thus leading to less computational overhead eventually. So more formally, what we want to specify are constructs of this form here. A set of affine expressions must lie in a potentially translated cone. And this can of course be just a small part or a building block of the whole program, and then you want to combine several of these building blocks. The challenge from the development point of view was to build an interface for that in a low-level language like C, and of course you want to be efficient in terms of computational time and memory usage. And the following few slides are about this challenge. The fact that we use a G vector here in the description and in the notation of the following slides is rooted in the idea of being able to reuse the same affine expression in several constraints with different right-hand sides. And this is then something that might contribute to the space efficiency of the new interface. Now, as a first step towards all this, we introduced the so-called Fmatrix, which is nothing more than a storage for a set of affine expressions. So you can basically keep a series of affine expressions in the interface from which to serve when building an actual optimization model. You can build your model using not all of the expressions in the Fmatrix, or you can use certain expressions multiple times. Of course, this is implemented so as to exploit sparsity. And one rule we impose on the Fmatrix is that affine expressions can never be deleted once they are added. And this prevents from having to update any reference to a certain affine expression because it changed its position in the Fmatrix, for example. So to make it very concrete, a set of affine expressions to be used in some part of the optimization model is not specified explicitly with data, but just by a list of indexes referring to the affine expression storage. That was the first step towards the new interface, and now comes the second. We further introduced the so-called domain storage, which is just a list of objects we call domains. Now, a domain is what you actually need to impose the structure of your Conic program, meaning linear inequalities or inequalities, and nonlinear cone membership. And a domain therefore always has a type, which could be non-negative, non-positive, or zero in terms of linear domains, or exponential, for example, in the nonlinear world. Also, the dimension is stored as an attribute of any domain, and if necessary, a cone parameter in case of the power cone, for example. Just like the affine expression storage, the domain storage lets you specify a list of domains from which to serve when specifying an actual model. And as in the affine expression storage, a domain can never be deleted from the domain storage. And now with these two things together, it should become apparent how a so-called affine conic constraint will be specified in MOSEK 10. It's just given by an ordered list of affine expression indexes, a single domain index, and possibly a G vector. And now to specify an optimization model, affine conic constraints are added together with the variables, and contrary to the affine expressions and domains in their respective storages, they can also be deleted in order to make it easy to, say, perform re-optimizations on modified models. For an affine conic constraint to be valid, of course, the dimensions of the set of affine expressions and the dimension of the domain have to match. But this is particularly easy to check given the way domains are implemented. Also, as anticipated earlier, it is, at least for MOSEK, important to be able to add new cone types in the future. But also that should not be difficult with the new interface. So all in all, we are quite happy with how all this was implementable in C, and of course with how it works so far. On the last few slides, let's see another novelty in MOSEK, and that is disjunctive constraints. And these mostly concern the interfaces, but partly also affect the underlying algorithms. Now, the idea behind introducing disjunctive constraints in the interface was to have a modeling construct that subsumes many special cases like semi-continuous variables, complementarity constraints, and many similar things. In a nutshell, they provide a means to model a choice over a set of generic alternatives. Also, the widely used indicator constraints, meaning that some binary variable z triggers a linear constraint when taking on a value of, say, 1, can be modeled as a disjunctive constraint. In fact, MOSEK's LP and MPS file readers have been extended to accept indicator constraints and to translate them directly to disjunctive constraints. Now, in practice, all these constructs are often modeled with the famous big M trick, and MOSEK makes extensive use of that trick internally. But there are still cases where this is not done, and a disjunctive constraint is thus not just a synonym for big M. Now, as for how to specify disjunctive constraints in the C API, it actually comes in handy to reuse the affine expression and domain storages. So a disjunctive constraint is just a list of affine expressions, now a list of domain indexes, potentially a G vector, and a list of disjunctive term sizes. Then everything is arranged sequentially, and the term sizes dictate where one disjunctive term ends and the next begins. So you can see then that a disjunctive term is basically nothing more than either exactly one or a sequence of several affine conic constraints. And of course, the dimensions of these assembled pieces have to match like in a single affine conic constraint, but this is again easily checkable given the way everything is implemented. So to sum up, the two big new things in MOSEK 10 will be affine conic and disjunctive constraints. Affine conic constraints are more general than what the interface offered before, and everything is nicely implementable in C. And also adding new cone types in the future is not a problem. Disjunctive constraints are very general and let the modeler get rid of big M's whenever that is desired. If you want to know more about MOSEK in general, please check out our website for lots of resources. There is the documentation section, for example, where you can get a free copy of the MOSEK modeling codebook. And you can check out many manuals and notebooks. And more code-related material can be found on our GitHub page. Now that's it from me. I hope you enjoyed this video, and thanks for watching.